Welcome back. Today we're going to be working on scientific notation day number 1. Content objective is students will be able to perform operation expressed in scientific notation. Language objective is students will be able to discuss patterns associated with the negative exponents. And why am I learning this? Well, it's important for real-world problems like comparing distances between planets. So first of all, let's talk about our central question. We're going to be thinking in the back of our mind through this entire lesson, how can we use properties of exponents to simplify expressions? So first, what is there to know about scientific notation? Well, number 1 is going to be formatted as such. A number times base 10 raised to a power, which I'm just going to call b. A, which I'm going to refer to as your coefficient, has to be between 1 and 10. Okay, it could be equal to 1, but it cannot equal 10. So examples might be 1.1 all the way to 9.99999. It cannot be 10, okay, because it has to be in between those numbers. Now, b, which is your exponent, could be any number. It could be negative or it could be positive. So scientific notation is a way to represent very large or very small quantities. So let me give you an example. This large number here can be expressed as 6 and 32/100 times 10 to the 9th. Now, real quick, we will go into how we got the number 9 and things like that. Here, this small number is represented by writing it as 2.7 times 10 to the negative 5th. And again, in a moment, we're going to go over how we got this particular exponent and this particular coefficient. So scientific notation is one of the very few situations in math or science where we actually leave our answers with negative exponents. Like you've seen here, we left it as a negative exponent. Normally we would simplify it and turn it into a positive, but this is the one case where you would leave it negative. So normalized scientific notation is the preferred way of writing it. Okay, so what is the purpose of scientific notation? Again, it is a way to write very large or very small numbers in a compact form, so it's easy for us to quickly look and say, oh, this is it's in the trillions or it's in the billions, etc. So, for example, the distance from Earth to Saturn is this many feet away. So notice we usually get comfortable reading numbers within thousands and maybe possibly the millions, but after that it gets a little bit difficult. So what's a quick way to see how far that it is in a nice compact form is scientific notation. This can be also written as 3 and 93/100 times 10 to the 12th power. Now, let's talk about something very small, like maybe the size of a hydrogen atom. Well, here is the size of a hydrogen atom. Very tiny. But again, a quick way for us to quickly look at a number and assess exactly how small it is without having to count how many zeros there are, we can express in scientific notation such as 1.0 times 10 to the negative 7th millimeters. So again, this is the only situation where we would keep our exponents negative. So you're going to see that positive exponents generally will represent a larger number relatively, and negative numbers are relatively going to represent small numbers. Okay, so we're going to write each number in decimal or aka standard form. So right now we're given a number in scientific notation. So one thing I want you to take a look at is the exponent. When the exponent is negative, it generally represents a small number. So in a case like this, we want to make sure our standard form is going to be a small number. So because it's negative, we're actually going to move our decimal point to the left. So first I'm going to start with my coefficient, which is 3.41. Now what I'm going to do is I'm going to go ahead and move to the left because we're making our number smaller. We're going to move it 6 bases to the left. So I'm going to move it once, twice, 3, 4, 5, 6. And now this is where my decimal is going to go. In these empty swoops, I guess you can call it, we're going to go ahead and place some zeros. So I would say this is my number in standard form. Okay, so notice there's 1, 2, 3, 4, 5 zeros, 1, 2, 3, 4, 5. Notice the number of zeros don't necessarily correlate to the exponent because some students assume that. So just please be careful about that. Okay, so what about the second one? Well, here our exponent is an 8, so our number is actually going to be a rather large one. So first we're going to start with our coefficient, which is a 6. So I'm going to write a 6. Now you have to figure out where is 6 in a whole number. Well, it always belongs at the end. Okay, a lot of students want to put it before, but that would be 6/10. Putting it here still represents this number as a 6. Now because this is a positive exponent, we're going to make our number larger. So the one way to make 6 larger is to move our decimal to the left or to the right. If you guessed the right, you are correct. So we're going to go ahead and move it 8 to the right. Just going to go 1. Hold on, let me switch colors here so you can see. 1, 2, 3, 4, 5, 6, 7, 8. So filling in these spots with a 0. So this would be my number. So I know it's a little messy, but what you could do is kind of separate them with your commas. It's a quick and easy way to tell how big your number is. So this is going to be our answer, 600 million. So notice even the commas kind of help us, but having it in scientific notation definitely helps us to quickly assess how big or small a number is. So same idea here. Since this is a negative exponent, our number is going to be small. First, we're starting with the number 7. And again, a lot of students often get confused of where our decimal is in a whole number. Let me real quick show you. If I put it here, does that look like 7? Hopefully your answer is no. That's 7/10. So that's not a good place to put it. What about after the number? Does that look like 7? The answer is yes. So you should always ask yourself that. Does it seem right? Does the number still represent the same number I was hoping for? So now that we have a decimal, we're going to go actually move to the left to make our number smaller. So we're going to move 6 to the left. 1, 2, 3, 4, 5, 6. And then go ahead and place zeros in between. Notice here, since the number is small, we don't use commas. So here, I'm just going to go ahead and write my number. Notice there is 1, 2, 3, 4, 5. And there's 5 zeros here. At this point, I would like you to go ahead and pause the video and try the next 3 problems on your own. Okay, so let's see how well we did. For number 4, hopefully you recognize that the decimal belongs after the 3. And since there is a negative exponent, hopefully you made the number smaller by moving the decimal over to the left 4 spaces. And your answer would end up as such. There should be 1, 2, 3 zeros just before the 3. Okay, number 5, hopefully you recognize that the exponent is a positive, so you're actually making your number larger. So in that case, you're going to move your decimal 7 places to the right. You'd be adding in 4 extra zeros, so your number is 56,420,000. And for number 6, here, since it's a negative exponent, hopefully you recognize your number is going to get smaller. But first you have to recognize where that decimal point is. It should have been after the 4. So moving a 7 over to the left, this would be your answer. Okay, so now we're actually going to do the opposite. Now we're going to take the number in standard form and we're going to write it in scientific notation. So if you recall from the beginning of the lesson, I talked about what your coefficient should look like. Okay, your coefficient needs to be greater than 1 or equal to 1, but it has to then also be less than 10. So think about it. I have some options. I can make it a 4.56, I can make it a 45.6, or a 456. But remember, meeting that requirement of it has to be either equal to 1 or less than 10, I'm definitely going to go with 4.56. So this is where I want my number to be. So let's see. I'm going to first start with 4 and 5600ths times 10, and I need to figure out to what power. So real quick, ask yourself, is this a relatively small number or a large number? Okay, I'm definitely going to say small. So because of that reason, I'm going to go ahead and say that it's negative. Now, this is where my decimal is. If you count to where it actually is, you'll notice you'd be moving 1, 2, 3, 4, 5, 6 to the left. And since we move to the left, that is going to be negative. Now, the tricky part is this. Some students are actually going to start where the decimal already is, and they're going to count all the way to where it should be. And they're thinking, oh, I'm moving to the right. It should be positive. But you should start with where you want it to be and then move to where it actually is. Okay, so let's try another one. So here, again, your coefficient has to be between either equal to 1 or less than 10. So the best option is to make it 4.9. So that's going to be my coefficient, 4.9 times 10 to the, okay, real quick. This is a large number, relatively large, or relatively small. Hopefully you're thinking that's a relatively large number. So this is where your decimal, where you'd like it to be, and it's actually way at the very end. So starting where you want it to be, go ahead and count how many spaces it would take to where it should. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8. And there you go. So again, the main thing is if you went the opposite direction and you started counting 1, 2, 3, 4, 5, 6, 7, 8 all the way to the left, and you're thinking, oh wait, I went to the left, that should be negative, you should think back and ask yourself, 4.9 times 10 to the negative 8, is that a small or large number? I would think that's small, and it doesn't reflect the number that's in front of me. So keep that in mind if you're ever unsure about that. Number 9. Okay, same idea. We need to first decide where should I put my decimal. Again, it has to be equal to 1 or greater, but it has to be less than 10. So I'm definitely going to go with 1.739. So that's my coefficient, times 10 to the, again, relatively small or relatively big. Definitely say relatively big. So it should be a positive number. So starting at where I want it to be and going to where it actually is, I'm going to count 1, 2, 3, 4, 5, 6, 7. So that is going to be my number in scientific notation. So the only thing you have to be very careful about is making sure your coefficient is between the range, which is equal or greater than 1 but less than 10. And the other thing is to make sure that your sign for the exponent is the correct sign. Is it positive or is it negative? So at this point, I would like you to go ahead and try the next 3 examples on your own, turning these standard form into scientific notation. I'm just going to quickly go over the answers. If you are not sure, please look at the work to see where things went wrong. So number 10, the answer is going to be 7.415 times 10 to the negative third power. So notice it is a relatively small number. That's why my exponent is a negative number. Number 11 is going to be 8 times 10 to the 6th power. And here it's a relatively large number, which is why we have a positive exponent. Number 12 is going to be 0.99 times 10 to the negative 5th. And it's negative because relatively it is a small number. Okay, so now we're going to actually go into working with scientific notation with different operations. The first one we're going to be working on is multiplication. So after we multiply, we want to make sure our answer is actually in scientific notation. So keep that in the back of your mind. So here is the given problem. What we're going to do first is use the commutative property to kind of figure out the new coefficient. So I'm going to multiply the 2 1/10 and 1 5/10. Those are the 2 coefficients. And then after that, we're going to actually go ahead and combine the 2 bases. So 10 to the 8th times 10 to the 6th. So what allows me to do this is the commutative property, because multiplication and addition both have this, where I'm allowed to rearrange things and it wouldn't affect my answer. Now, real quick, I am just going to remind you how to multiply decimals. It's been a while. So just a quick refresher, we're going to do 2 1/10 times 1 5/10. The multiplication part shouldn't be the hard part. It's just remembering where my decimals should go. So after multiplying, I end up with something like this. Here, you want to count how many decimal places there are. So there is 1, 2 altogether. So you're going to move your decimal 1, 2 spaces. So I'm going to have 3 1500ths times 10. Now, calling back the information about properties of exponents, what do we do when the bases are being multiplied? Well, we're supposed to add them. So 8 plus 6, that's what we're going to do. And then our final answer would be 3 and 1500ths times 10 to the 14th power. Now we're supposed to check. Does this follow the scientific notation where the coefficient is equal or greater than 1 but less than 10? Yes, that definitely does. So this is actually going to be my final answer. So from there, I'm going to quickly remind you how to start one, and then I'm going to have you actually finish number 11 and 12 on your own. So just to start you off with number 11, what we're going to do here again is we're going to multiply the coefficients together. So 8 times 1 and 2 tenths, and then you're just going to also then multiply the base 10s together. So 10 to the 14th and 10 to the 11th. So here I'm just going to actually stop there and have you finish off number 11 and also try number 12 on your own. Okay, so let's see how well we did. Hopefully you multiply the two coefficients together and got 9 and 6 tenths. And then you combine the base 10s together. Since we are multiplying, you get to add the exponents, leaving you with 9 and 6 tenths times 10 to the 25th power. Now this is in scientific notation because the coefficient follows the requirements of it's definitely greater than or equal to 1, but less than 10. Okay, then number 12, hopefully you went through that one as well. First collecting the coefficients, 1 and 3 tenths times 4, and then collecting the base 10s together, 10 to negative 7, 10 to negative 9th. Multiplying the coefficients together, you should have gotten 5 and 2 tenths. And here, combining the exponents together, put parentheses here. Since we're multiplying, you can go ahead and add the exponents once more, leaving you with a final answer of 5 and 2 tenths times 10 to the negative 16th. And once again, with scientific notation, it is perfectly okay with having negative exponents. In fact, you're supposed to leave it as a negative. Okay, so now we're going to move on to a different type. Now we're still going to be working with multiplication. Now you're probably wondering, what do you mean by another type? Well, in certain cases, like this one here, if I multiply the we're going to go over the same steps. We're going to combine the coefficients by multiplying them together. And then we're also going to combine the bases by multiplying them together. Hopefully you have the multiplication down. Here you're going to get 19.142 times 10 to the, well, there's 7 here, 8 here, so there's 15 altogether. Now, here's the type that I'm referring to. Notice this answer is not in normalized scientific notation. How come? Well, because our coefficient is too big. It's 19. The boundary is either greater or equal to 1 or less than 10. And this is definitely not less than 10, so we're going to have to adjust it. Now, how can I make this less than 10? Well, you could move the decimal over once, making it 1.9. That would then be in scientific notation. Notice, whoops, by me doing that, I'm technically making the number smaller. I went from 19 to 1.9. Okay, so if I'm making this smaller, I need to balance things out, which means I'm also going to have to make this side larger. Okay, so here's what you do. In a sense, when you are making this smaller, you're technically multiplying it by 10 to the negative 1, which is the same as dividing by 10. But to keep things balanced, I'm going to then have to multiply this by 10 to the first power. Okay, so again, it's all about keeping things, whoops, when one's going smaller, the other one's getting larger. But I would rather you think of it in terms of exponents since we've been working on it a lot. So here, I'm multiplying by 10 to the negative 1 to balance it out. I'm multiplying this side by 10 to the positive 1. So I'm going to be left with 1.9142 times 10 to this, since it's getting 1 larger. You would be adding the 15 and the 1 together, which gives you 1.9142 times 10 to the 16th power. let's get a little more practice. So again, we're going to go ahead and be asked to multiply these scientific notation problems. First, what we're going to do is combine the coefficients together. So you're going to multiply 7 and 4/10 by 3 and 3/10. And then you're going to combine the 10 to the 10th power times 10 to the negative 5th. So multiplying these coefficients together, you're going to get 24 and 42/100 times 10 to the, well here since it's being multiplied, using the property of exponents, I'm just going to add these exponents together, leaving me with 24 and 42/100 times 10 to the positive 5th power. Now, unfortunately, I can't stop, mainly because this coefficient doesn't fulfill the requirement of being greater than or equal to 1 or less than 10. This is bigger than 10, so I'm going to have to adjust it. I'm going to have to make it smaller by making it 2.4 instead of 24. So I'm making it smaller by multiplying it by 10 to the negative first. And to balance things out on this part, okay, I'm not going to say side because that's going to be a little confusing. To the 10 to the 5th, I have to do the opposite of it to keep things balanced. So I'm going to multiply it by 10 to the 1st power. So now that's going to leave me with 2.442 times 10 to the 5 plus 1, because I'm going to add the 5 and the 1 together, leaving me with 2.442 times 10 to the 6. So a quick and easy way of saying it is, hey, if I'm making this one smaller, I'm going to make this one larger. But I would rather you think of it in terms of exponents, because essentially what's happening is this is being divided by 10, so this needs to be multiplied by 10. Okay? So now I'm going to go ahead and start you off with, actually I'm going to go ahead and do number 14 as well. That way you can try numbers 15, 16, and 17 on your own. So same steps as before, we're going to rearrange it using the commutative property by grouping the coefficients together and then the base 10s together. So multiplying the coefficients together, I'm going to get 24 and 5/100 times 10 to the, here since they're being multiplied, I can add the exponents together, leaving me with 24 and 5/100 times 10 to the 18th power. Now I can't stop yet because my coefficient is too large. I'm going to need to make it smaller by moving it once over to the left. By making it smaller, I'm essentially multiplying it by 10 to the negative first. Or you can think of it as I am dividing by 10, because that's what negative exponents represent, repeated division. And then because I'm changing my coefficient, I need to adjust my base to adapt to make it so that I'm not changing the value of the number at all. So I'm actually going to multiply it by 10 to the positive 1. Why is this okay? Because 10 to the negative 1 times 10 to the 1st power is 10 to the 0. And what's 10 to the 0? 1. So I'm essentially multiplying it by 1. So I'm not changing the number at all. Okay, so some of you may be arguing like, why don't you do the same thing to both sides? Well, if I multiply this by a negative as well, I'd be essentially multiplying this entire problem by 10 to the negative 2nd. Now that would definitely change the value of my number. But because I'm balancing it out to 10 to the 0 power, which is just 1, I'm not changing the problem at all. I'm just making it look different. So from here, I'm going to get 2.405 times 10 to the 18 plus 1, which is going to give me 2.405 times 10 to the 19th power. Okay, so at this point, go ahead and pause the video, and I want you to try numbers 15, 16, and 17 on your own. Okay, so let's see how well we did. Number 15, hopefully you rearranged using commutative property, rearrange the coefficients together and the 10s together. Then you multiply the coefficients together, giving you 83 and 42/100 times 10 to the. Here, since the bases are being multiplied, you can add them together, leaving you with 83.42 times 10 to the negative 11th. Here, you have to be careful. Again, this is not following the requirements. I need to make this number smaller. So essentially, you're multiplying it by 10 to the negative 1. Again, it's also dividing by 10, whichever way you want to think of it. So to keep things balanced, I need to multiply this 10 to the negative 11th by 10 to the 1st power, because you're making it larger. And again, what's 10 to the negative 1 power times 10 to the 1 power? 10 to the 0. And what is 10 to the 0? Just 1. So multiplying a number by 1 doesn't change it at all. So now I'm going to be left with 8.342 times 10 to the, be very careful. What is negative 11 plus 1? Okay, that's going to give me a negative 10. Please don't accidentally put negative 12. That's going to be a little error that you're going to make at the very end that's going to ruin your entire answer, so be very careful. Okay, so let's take a look at number 16. Same idea. Let's group the coefficients, group the base 10s, multiply the coefficients, combine the exponents, leaving you with 12 and 8100ths times 10 to negative 12. This number's too big. I need to adjust it, so I'm going to move it from 12 to being 1.2. By doing that, I made the number smaller, so I'm going to multiply by 10 to negative first. To keep things balanced, I'm going to multiply this 10 to the negative second by 10 to the first power, because again, these two numbers multiply together is 10 to the 0, which is just 1, so it doesn't affect anything. Okay, so from there, my answer is going to become 1.281 times 10 to the negative 2 plus 1. Negative 2 plus 1 is a negative 1, so just be very careful and make sure you're doing that arithmetic correctly, because there's nothing worse than messing up at the very end. Number 17, multiplying the coefficients first, then multiplying the bases. And here's what we have. Our base is too big, so we're going to have to make it smaller. In this case, we are multiplying by 10 to the negative first. Because of this reason, I'm going to have to make this side balanced by multiplying it by 10 to the positive 1. So now we're going to end up with 1.176 times 10 to the 0 plus 1. Okay, and then that's going to be 1.176 times 10 to the first power. So that is actually going to conclude the lesson for today. Thank you so much for tuning in, and as always, until next time, bye.